and welcome to this lecture. We're going to look at straight lines a bit more analytically. So, if you remember the previous lecture, we looked at graphical solutions for equations involving straight lines and quadratics. We saw that we could obtain the solution, but there's a little bit of unsettling thing about that because we had to do some scaling carefully here, there, and all that. Or maybe that's not the most comfortable thing in the world. So, one good thing would be to see if we can avoid the graphical method and write down equations and try and do computations that way. So, that way maybe one can quickly get to the answer, and it's also a very interesting way to understand more about what these straight lines are. So, let's get started. Here's the equation of a straight line. We've seen that before. Y equals mx plus b. The 0 comma b is the y-intercept on the line, and then m controls the slope, right. So, m is positive. As it goes higher, it goes steeper and steeper and steeper, and if it goes negative, it's the other way, etc. So, I've just shown a generic straight line. Now, it turns out the slope is also connected to any 2 points on the straight line. So, this is a critical property of the straight line. If you take 2 points on the straight line, you can compute the slope of the straight line, and there is a very simple relationship for it, and it can be very easily derived. And I want to show you that sort of graphically and as an expression, so that you see how the slope is connected to 2 points on the straight line. So, this is an important idea, and it will come back to us again and again and again. So, on any curve we will try to define slope and all that, but for a straight line it's very easy to compute the slope given any 2 points, and let's see that. That's the starting point of the computation. So, here are 2 points. I have shown them, x1 y1 and x2 y2. Both of these points are on the straight line, right. So, both of them satisfy the equation y equals mx plus b. So, you have y1 equals mx1 plus b, y2 equals mx2 plus b. So, now we will start manipulating these relationships. So, this is a very simple relationship that's satisfied by 2 points on the straight line, and we will use our mathematical approach where we will manipulate this relationship to derive slightly better relationships. And what we want is we want slope to be calculated given the 2 points, right. I want to calculate m alone in terms of x1 y1 x2 y2, and I have this equation. So, a very interesting thing to do is to get rid of b is to subtract these 2 equations, right. So, it's sort of clear from this. So, you can subtract these 2 equations. If you subtract these 2 equations, you get y2 minus y1 equals m times x2 minus x1. I hope you see this, how I have manipulated this equation to get this. You get this very simple and wonderful relationship for slope in terms of the 2 points x1 y1 x2 y2. You can actually relate it to the graphical picture as well. If you draw this sort of triangle, so you see x1 y1 x2 y2, where is y2 minus y1? It's the length of the height difference between these two, right. So, that's that one arm of the triangle, and then x2 minus x1 is the other side of the triangle. You have this right angle triangle, and the slope is simply y2 minus y1 by x2 minus x1. This is true for any 2 points on the straight line. Okay, I have shown it for x1 y1 x2 y2, arbitrary 2 points. You take any 2 points on the straight line, you are going to get the slope being y2 minus y1 by x2 minus x1. Okay. So, this is a very nice and simple relationship. The straight line has the same slope wherever you go, and you take any 2 points. However far the 2 points are, the slope is always the same. Okay. It's a unique property of the straight line, very important property. It helps us quite often later on, you will see. Okay. So, now I have computed slope from 2 points on the straight line. Okay. Now, it's also true that 2 points on the straight line completely define the straight line. Okay. So, can I do anything more with it given 2 points on the straight line? It turns out it's true, and that's what we're going to do next. If you just look at 2 points, okay, and ask the question, what is the straight line that connects these 2 points? Okay, what is the equation of the straight line that connects these 2 points? That's a question you can ask. We've already found the slope, right. To find the equation of the straight line, I need the slope m and the y-intercept b. I have to find the y-intercept b. Given the 2 points, I know how to find the slope. That I have done already, right. Slope is y2 minus y1 by x2 minus x1. Can I find the y-intercept? just given 2 points on the straight line. Somewhere I've given 2 points on the straight line. Can I find the y-intercept? Turns out yes. And here once again we start with this basic relationship and try and use the same idea in a clever way to derive the next relationship. Okay, so let's do that next. Here comes the clever idea. So I know for any 2 points on the straight line, we take the slope calculation and we try and repeat it for the another set of 2 points on the straight line. So this is the clever idea. This is a logic and this is a slightly clever step. And you see that this gives you the y-intercept in a very indirect sort of smart way. Okay. So what do I do here? I know that x1, y1 and 0, b are also on the straight line, right? 0, b is the y-intercept. So 0, b is on the straight line, x1, y1 is on the straight line, x2, y2 is also on the straight line. So I can use x1, y1 and 0, b. And what do I know? I know the slope is also given by b minus y1 by 0 minus x1. Right? For any 2 points, slope is given by difference of the y coordinates divided by difference of the x coordinates. So I use that formula and I get slope to be equal to b minus y1 by minus x1. I already have one expression for slope above. I have another expression for slope below. I can equate the two. So notice how logically, in a very simple way, we're able to use these basic relationships over and over again and derive more and more and more interesting simple relationships. So this is the method of mathematics, and it's wonderful to see how powerful it is. So y2 minus y1 by x2 minus x1 is the same as b minus y1 by minus x1. You cross multiply and then move the y1 to this side, you get b equals a formula involving x1 y1 and x2 y2 alone. Okay, isn't that wonderful? So we've got given 2 points x1 y1 x2 y2. I am now able to calculate the slope of the straight line that is passing through these 2 points. I am also able to calculate the y-intercept of the straight line that's passing through these 2 points. Okay, it's a very simple calculation. There's no need to mug up the final formula. A lot of people will end up mugging up the final formula blindly. They won't know where it comes from, and when they have to use it or when they have to use it in a new situation, they get stuck. So you should just know that the logic is very simple. Given 2 points, you can calculate the slope. That's it. In the straight line, that is the most important principle. And then once you use that principle over and over again, you get everything else. So you have m, you have b, so you can do the straight line, right? So this is a simple enough thing. Y equals, right? This is the equation, no? Y equals mx plus b. So this guy is m, right? This guy is m, and this whole thing is b. So this is how the equation comes. So you see, you get a y equals mx plus b, and you find a straight line equation through these two things. Okay. So now it's this equation. It's fine. It's a nice equation, but you can write it in a slightly different way. Sometimes the same equation written in a different way is easier to remember. So a lot of people write the same equation in this format. Y minus y1 by x minus x1 equals y2 minus y1 by x2 minus x1. This is the equation of the straight line passing through x1 y1 and x2 y2. And it's a small exercise for you to show that these two are exactly the same. It's just a small different cross multiplication and you get the same maths. Okay, it's a simple exercise. Try it. You can prove that it's true. Okay. So look at all that we're able to do. Given 2 points, x1, y1, x2, y2, you can find the equation of the straight line passing through those 2 points. And it hinges critically on the fact that slope simply is the difference between the y coordinates divided by difference between the x coordinates of any 2 points on the straight line. Simple, isn't it? So you start from a very basic simple relationship and we can derive non-trivial relationships starting from that point on. Okay. Okay, so here is an example. I could just do this in good detail. I'll just do at least one question in good detail and then you can see how the other things go about. Finding the equation of a line through each of the following pair of points, 3, 4, 5, 10. It's easy enough to try that. Let's go through and do that. Line through 3, 4 and 5, 10. It's a easy enough formula. I really like this formula. I can remember this anytime. y2 minus y1 by x2 minus x1. So this is x1, this is y1, this is x2, this is y2, and at this point you're done. You know, I mean, you can see y minus 4 by x minus 3 is 10 minus 4 by 5 minus 3, 6 by 2, that's 3, and you can go through and simplify this. I hope I don't make any mistakes here. 3, so you get y minus 4 is 3x minus 9 and y equals 3x minus 5. Okay, so this is the answer. So that's the slope, that's the y-intercept, and you can see that's the equation of the straight line. It passes through a quick way. At this point you can go back and check. You put y equals 4, x equals 3, you get 9 minus 5 is 4. If you put x equals 5, you get 15 minus 5 is 10. So it passes through 3, 4 and 5, 10. Quick way to check that your answer is reasonable in some way. Okay, so you can do the same thing for the other problems. So you can find the equation of a straight line given any 2 points in it. Just 2 points in a straight line define the straight line completely. Okay, so it's a nice thing to see. Okay, so let's move on and try and see if we can push this a little further and try and solve for point of intersection of two straight lines. Right, this is what we wanted to do to solve that first problem involving the shopping problem. Involving the shopping person and who wanted to buy apples and oranges. We had this very nice problem. So let's see if we can do this. So here I've shown equation of two straight lines which seem to be intersecting at some point. Okay. The question is, can I derive an analytical expression for what that point of intersection should be? Okay. So that's the question here. Let's say the point of intersection is x0, y0. The key logical point here, which is sort of easy to see, is that the point of intersection lies on both the lines, on both y equals m1x by x plus b1 and y equals m2x plus b2. So you put in x0, y0 in, you're going to get y0 equals m1 x0 plus b1. I really like y0, you know, y0 is why not, why not? Right? We always keep asking why, we should also ask why not. Anyway, it's not the main point here. This y0 is y0. Okay, y0 is m1 x0 plus b1, y0 is m2 x0 plus b2. And how do you solve these two equations? There are two equations, two variables, and what do I do next is the interesting thing. Both of these are expressions for y0, right? So why not equate these two things, right? So let's try that. So m1 x0 plus b1 should be equal to m2 x0 plus b2, isn't it? So this is one equation and one variable and just a linear equation. We know how to solve this. We can manipulate it around, and you see x0 is b2 minus b1 by m1 minus m2. So notice this, the way in which it works. Very simple solution, isn't it? So the x0, the x point of the intersection, we are able to derive, we are able to compute involving just the two equations, right? m1, m2 and b1, b2. So notice once again, we start with basic relationships, manipulate them to get the next level of relationship. There's no need to mug up these formulae at the end, right? So it's, if you know the basic relationship, you know the logic, you know the quick derivation. It's very easy. Okay. Once you know x0, how do you find y0? You substitute it back into this equation, any one of these equations. You pick your favorite equation. I picked the first one. You can pick the second one also. You'll get the exact same answer, believe me. So you get y0 equals m1 times this x0 plus b1. You can now, you know, do this manipulation. You'll see something will cancel, something will not cancel, and you'll get y0 as m1 b2 minus m2 b1 by m1 minus m2. Okay. So very nice, simple expression, and you're able to see the point of intersection of two straight lines. You don't have to compute graphically, you don't have to go to Desmos. You can write down the equation here using your calculator. You can exactly find where the x-axis x0 is, y0 is, where is the x comma y on which two lines intersect given their equation. Very simple idea. Okay. Let's solve maybe one problem here. Let me just pick up one problem and try and solve it for you. I'll take the first one. First one is really easy, and I'll also maybe do the second one just to show you how the second one works. We'll try, maybe we should quickly try all of these things. These are interesting questions. So let's try the next problem. Y equals 3x plus 4. Did I get that right? Let me just make sure I do it right. 3x plus 4, 4x plus 5, right? So y equals 4x plus 5. See, I can go back and of course mug up the formula and remember it and do that, but there's no reason to do it, right? So if x naught, y naught is the point of intersection, it is there on this line, it's also there on this line. So I'm going to equate these two things, right? So 3x naught plus 4 is 4x naught plus 5. How easy is this, right? So x naught is minus 1. So you get that, and from there y naught is 3 times minus 1 plus 4, which is plus 1. Okay. So the point of intersection is minus 1 comma 1. You can quickly check that if you put minus 1 comma 1, you get this line as well as this line, right? So x equals minus 1 gives you y equals 1 here, x equals minus 1 gives you y equals 1. How simple is this, right? So you can very quickly do this. Let's do the second problem. Second problem is, it's given in a slightly different way. Let's write it down and then we'll do the other way. So the problem is given as 2x plus 3y equals 4, 3x plus 4y equals 5. So I like it written like this, right? So let's rewrite this. This is y equals minus 2 by 3x plus 4 by 3, isn't it? So 3y is minus 2x plus 4, and then I divide by 3, I get it like that. So this step is a simple manipulation, but you should get comfortable with this one. So this is very important. And here also, I move this to this side and then divide by 4. I get minus 3 by 4x plus 5 by 4. Okay, now I'm back in this whole territory. So if I have x naught, y naught as the point of intersection, minus 2 by 3 x naught plus 4 by 3 equals minus 3 by 4 x naught plus 5 by 4. So move this to this side, move that to that side. So you get 3 by 4 minus 2 by 3 x naught equals 5 by 4 minus 4 by 3. Let's do this fractional computation. So this is a good, the common denominator is 12. I can just multiply these two, 4 into 3, 12. 9 minus 8 is 1, so 1 by 12 x naught. Here again, 12, 15 minus 16 is minus 1 by 12. So you get, voila, x naught equals minus 1. So once you put x naught equals minus 1, y naught is going to be minus 2 by 3 times minus 1 plus 4 by 3, and that is 2, isn't it? So you see minus 1 comma 2. Once again, you can check minus 1 comma 2 is plus 4, minus 1 comma 2 again is plus 5. So it works out correctly. It passes through these 2 points. So minus 1 comma 2 is the point of intersection. Okay. So the next 2 questions are a bit interesting here with straight lines. Something curious will happen here. That's why I put that as an example. X minus 3y is 4 and 2x minus 6y is 6. So these are 2 straight lines. X minus 3y is 4, 2x minus 6y is 6. I've carefully constructed this, these 2 examples, and let's follow the method blindly, right? So we have a method, we're going to follow it blindly. Let's say we assume that these 2 lines intersect at x naught, y naught, and then try to find x naught, y naught, right? So this is our assumption. So notice the logic here. When you make an assumption, this assumption can be wrong. Maybe these 2 lines don't intersect, right? So they could be parallel, we know that. But right now we are always assuming they intersect at x naught, y naught. So when you make a wrong assumption and carry on with a mathematical simplification, you will end up with some sort of contradiction, right? So that's okay. So if you see a contradiction, then we'll go back and see what's wrong. Okay. So you should always keep that in mind. You have to be very logical about this sequence. We are assuming x naught, y naught is the point of intersection. Let's proceed and see what happens. Like I said, this is a carefully constructed example. So you will get y naught. So this equation, so I'll write it out in the other format. Y equals this way, x by 3 minus 4 by 3, and then y equals, so you get here, this goes here, this goes there, you get x by 3 minus 1. right. So, these are the two equations. So, if you write down x naught y naught, you get y naught equals x naught. No, so you can just blindly equate these two, right. So, x naught by 3 minus 4 by 3 equals x naught by 3 minus 1. Guess what? X naught by 3 cancels here, and you get this really ridiculous statement that 0 equals 1 by 3, which is a contradiction. So, by a logical argument starting with these two equations, you are getting a contradiction, which means some crucial assumption you made in the beginning is wrong, or somewhere along the way is wrong. Okay, the only assumption I made is the lines intersect at x naught y naught. After that, everything else was direct deduction. I didn't do any mistake there. So, lines intersecting at x naught y naught maybe is not true. Okay, so it turns out that is correct. These two lines are parallel. Okay, I will give you an exercise here. Go to desmos.com and check that. You sketch these two lines, you plot these two lines on Desmos, you will see they are indeed parallel. They don't intersect. Okay, so these methods that you derive, you have to be very careful, right? You assume something and then you derive. Yeah, it's great. When that assumption is true, you will get the correct answer. If you end up getting a contradiction, you should go back and check whether something is wrong with that assumption, or this type of question doesn't really follow. Okay, so here is a very nice example where that happens. Let's see the last one. The last one is also interesting. 3x minus y is 4, 6x minus 2y is 8. That will close. 3x minus y is 4, 6x minus 2y is 8. Okay. Once again, we will assume that these two are going to intersect at x naught, y naught. Okay, this is our assumption. And then we plug in here. So, here there is a slightly different case. You will see where this comes from. Let us write this equation down. You are going to write y equals 3 by 4x minus 1 by 4, right. This is this equation. So, you look at the first equation, take y to this side, 4 to this side, and then why am I dividing by 4? I am sorry, this is not correct. Y equals 3x minus 4. That is it. That's what I want. Sorry. So, here you take 2y to this side, 8 to this side, and then divide. Guess what you get? Y equals 3x minus 4. Okay. So, it is the same equation. You can do this ridiculous thing of 3x naught minus 4 is 3x naught minus 4. You get 0 equals 0. Okay. So, what does that mean? Curious, isn't it? Both these equations are exactly the same. These are identical equations. So, what happens when you have identical equations? You can try plotting these two things. You will see the two lines will perfectly overlap. Okay. So, it means these two lines intersect not only at one point, they are the same lines. So, they intersect everywhere. So, any x naught you can find a y naught. Okay. So, any x naught or all x naught and y naught equals 3x naught minus 4 lies on the line, which means it lies on the other line also. Both the lines are exactly the same, right. So, these are the two, both equations are exactly the same, they are not different. Okay. So, sometimes this can also happen. You start with assuming one point of intersection, and guess what, you get all the points of intersection through your analysis. Okay. So, such interesting things can happen even with the straight line. We will come back and revisit this at a later time. Okay. To summarize, we saw 4 different examples. The first 2 gave you unique intersection points. The third one actually ended up being parallel lines. So, there is no solution, there is no intersection, and the same method we saw gave you that answer also. Carefully, when you look at it, you got a contradiction and you got that method. And then the last line is actually same equation written differently, and when you solved it, you found that you got a trivial relationship, 0 equals 0. So, which means all points on the line are points of intersection between these two lines, right. They lie on the same, both lines are on top of each other. Okay. So, notice how the analytical method, carefully considered, can take care of all these types of situations. Okay. So, hopefully you are convinced that the analytical method dealing with straight lines and their points of intersection, the fact that the slope can be computed using 2 points, the y-intercept can be computed using 2 points, the equation of the straight line through 2 points, all of these are very, very useful going forward in this course. Okay. So, now that we know so much about straight lines analytically, let us go back and revisit our wonderful problem with which we started this week's lecture, the shopping problem, where we had 2 equations, and let us see if we can analytically solve it using the method that we have here, right. So, this is our equation. So, let us see if we can start with this equation again and solve it. Let me see, I had done this before. Yeah, there you go. So, we had done this graphically. Let me go back to this first equation and try and do my analytical solution. Okay, so what is my two equations? X plus y equals 5, 2x plus y equals 8. I can very easily do this, right? So, if these two are going to intersect at x naught, y naught, let me write it differently. Y equals minus x plus 5, y equals minus 2x plus 8. You can do this very quickly now. Minus x naught by 5 equals minus 2x naught plus 8. Move this to this, move this to this. You see x naught is 3 and y naught is 2, right? So, this is what we wanted. Solution is 3 comma 2, which is the same as the solution we got using the graphical method. Okay. So, finally we are able to completely fully solve this problem analytically and get the answer we want: 3 kgs of apple and 2 kgs of orange. That concludes this lecture. We will meet again in the next one.